Good afternoon, everyone. My name is Ziyuan Gu, or you can call me Frank. I'm working with Dr. Miad and Professor Travis on the topic about pricing, as indicated by the title here. So the motivation of choosing pricing as my research topic is probably due to the fact that, well, most of the cities nowadays experience very severe congestion problems. And of course, pricing is not the only possible solution. Well, traditionally, we try to expand and build more infrastructure to solve the increasing demand. But unfortunately, that's not a long-term sustainable solution because of the induced demand. And so pricing is among one of those we usually termed TDM or traffic demand management policies, which use an economic level to influence travelers' behavior to achieve a certain objective. And that's what I'm actually working on. So the outline of the presentation today is very regular, consists of 5 parts from introduction, which will give you a very brief definition of what is road user pricing and what is congestion pricing, followed by a literature review. And I guess the main part is the methodology part, which tries to optimize a toll rate to achieve a certain objective. And following the methodological part, I will present some of the results and discussion. And finally, I'll touch a little bit on a quite interesting topic, at least from my perspective, which is called toll area problem. So as I said, congestion is nowadays very severe in different cities, and in the Australian context, it's the truth. We are experiencing tremendous economic loss due to urban traffic congestion, and obviously Sydney and Melbourne are experiencing the most congestion problem in Australia. In fact, I totally agree with this figure because I was reading my PhD in Monash, Melbourne, and when I came to Sydney, the first impression is that Sydney is so much more congested than Melbourne that I don't really want to drive here. And so I totally agree with this figure. So when we say road user pricing, we consider it as a type of transport pricing which imposes direct charges on road use, which obviously includes toll roads and parking fees and some other forms. And there could be many possible objectives for introducing road user pricing. For example, we want to manage demand, we want to reduce road congestion or increase speed, or improve air quality and raise revenues. So generally, when we try to introduce a road user pricing policy that tries to achieve the first 3 objectives, we usually term this policy as a congestion pricing. Well, whereas when we say we want to improve air quality or simply raise revenues, we just say it road user pricing. So in theory, there are generally 2 categories of pricing methods. One is the first pricing. One is called first best pricing, and the other is called second best pricing. So basically, first best pricing means that we are trying to charge every link in a network so as to achieve a system optimum objective. And usually, the amount of money that is charged on the link equals to the gap between the marginal social cost and the marginal public cost. So intuitively, it tries to charge users an amount of money so that users are aware of their travel impacts on others. Because basically, when we make travel decisions, we don't care about the impacts on others. So when we model and especially we want to achieve system optimum, we need to internalize this externality, and usually we term this congestion externality. But unfortunately, in practice, first best pricing is not very popular because, as I said, it requires charging every link a certain amount of money. And in practice, it's not very feasible. So as an alternative, there are multiple second-best pricing regimes where we only charge a certain part of the network. And these are several regimes. And here's a very simple graph representation of these different regimes. So for example, if we have a city center, a link-based regime simply means that we only charge an individual link, or an individual link. It could be a corridor, it could be a tunnel or a bridge. And when we say zonal or cordon-based pricing, we are looking at an area, and the only difference between these two is that for zonal pricing, we also charge trips that occur within the city center, whereas in a cordon-based regime, we only charge trips that cross the boundary of the city center. So of course we have another two regimes which are more specific. One is distance-based and the other is time-based. So distance-based regime means that the price is simply based on the distance traveled. So the more you travel, the more you pay. And time-based means that the price is based on time. So there are actually quite a few implementations nowadays in the world regarding congestion pricing. And I guess the most recent development is the Oregon one in US. So the system in Oregon is currently a statewide pricing system, and it's an open system, so users can choose to enter the system or choose to stay in the original system. So if they choose to enter the new user pay system, they pay according to the distance traveled within the network instead of paying those taxes. Whereas for those who choose to stay in the system, they still pay their taxes, but they don't pay for the kilometers they travel. So this is the most recent development. But on the other hand, I also want to mention this the electronic road pricing in Singapore because it's very famous. It's actually the first one implemented, and there will be an upgrade on this ETC system in Singapore from 2020 onwards. Now it's more of a cordon-based regime. So you pay per entry, but from 2020 the system is going to upgrade to a distance-based using satellite. So then the pricing system in Singapore is quite similar to the one in Oregon. I guess these two will be from my perspective, will be the state-of-the-art practice in terms of road pricing. From theoretical point of view, of course, we do have a lot of pricing studies, mainly using traditional bi-level optimization method. But since we are looking at an area, it would be, intuitively, it would be more comfortable to use some sort of network-wide measurement to study this road pricing topic. And with the finding of the network fundamental diagram or macroscopic fundamental diagram, we do have a new branch of pricing, which actually facilitates the large-scale pricing because of its macroscopic nature. And generally, there are two methods. One is to extend the bottleneck model by considering the capacity drop, which is modeled by the MFD. And such a method is tries to model the within day dynamics because the bottleneck model uses the cumulative departure and arrival curve. So the resulting pricing is real time. And on the other hand, there's a second category of method which basically tries to use feedback control theory to optimize the toll rate. And under this category, the resulting pricing strategy is not real time. It belongs to the day-to-day dynamics category. And basically, well, at least considering the existing literature, there can be two types of this feedback control concepts. One is the so well-known PID controller, which is a well-known controller in control theory, and the other is the traditional marginal cost pricing. So, of course, as indicated by my topic, I'm using NFD to do my research. So I guess all of you may have an idea of what is MFD because Mia has already introduced a bit about it. And so I won't go into detail, but the point here is that by using MFD or NFD, we don't need to care about the detailed link past all the information because we are solely looking at an area, which is of course modeled by this NFD. And so in general, when we try to use MFD to control a network, the common objective is to control the MFD within the left part of these curves. So because the left part represents the flow regime and the capacity regime, and obviously we do not want to enter the congestion regime or gridlock. So in my research, I tried to propose a new joint distance and time toe using NFD as an indicator. And it's actually a quite simple method concept. It is a linear combination of a distance toe and time toe. So there are three simple equations here. The first one tries to calculate the distance toe. So you can see the summation here is the distance you traveled within the cordon multiplied by a toe rate. And the second corresponds to the time toe. So when you incorporate these two toes into your original travel time, you obtain a generalized travel cost function, which is further incorporated with C-logic stochastic Rothschild model. I'm using this model because I'm using MSUM simulation, and this C-logic model is a model provided by the software. So I'm not using any other Rothschild model. So as I said, I'm using simulation, and the simulation is so the model I'm using is a model of Melbourne. I'm sorry about that because given my previous situation, that I'm using the model of Melbourne rather than the model of Sydney, and basically the model looks like this, which is deployed in MSUM. The model is calibrated using multi-source data, but all the credits are not mine. So this part of the work belongs to one of my previous colleagues named Sajad. So all the calibration and all the calibration works here belongs to him. So I'm simply using that. This is just a brief summary of the OD demand calibrated from the traffic data. And these are some statistics regarding the entire network. So in my case, I'm not using the whole network because that's too big and takes quite a lot of simulation time. So I extract part of the network and use this subnetwork to study my pricing strategy. And as you can see from this figure, this small rectangle represents the CBD area of the Melbourne, and I use it as my coordinate area. And this is the OD demand. So similarly, this is some statistics regarding this simulation subnetwork. So finally, the way I'm trying to update or optimize my toll rate is to use this feedback control strategy, which is called PI controller. So the mathematical expression is actually quite simple. It's just a summation of three terms. And so alpha here is the toll rate, and I here represents the iteration. And KP and KI are parameters adjusted through trial and error. And K max is the maximum density within your tolling period obtained from simulation. And KCR is the critical density obtained from your MFD, which is used here as a threshold. So you try to control the network so that the resulting maximum density does not go beyond the critical density. And of course, there are some mathematical derivations behind this controller, but I think that's not important. So the importance is that when using this type of PI controller, it has several properties, and which is actually quite good. Of course, the first one is that when you use it, you can control the system to your optimal state, which is specified by your critical density. And as I said, the Kp and the Ki are proportional and integral parameters. And when you have moderate changes, the controller still works fine. So it has robustness. And of course, there is evidence have shown that this controller has fast and global convergence. So finally, I have this simulation-based optimization framework, and I use this framework to obtain my optimal toll rate. So you can see I first use the controller and then obtain the price, and I input the price into the simulation, and I run this iterative loop. So these are the results. So here the JDTT represents the joint distance and time toll. And I also add the distance toll here. So because of the time, I'm going to focus on a few things. So first, from these results, the very important observation is that under the distance toll scenario, travelers tend to accumulate themselves into the shortest path in the code, as long as the utility from paying a lower distance toll dominates the utility from the increase of travel time. So this can be seen from the first graph, where the distance toll scenario gives you a much severe hysteresis phenomenon, because users tries to accumulate themselves in the shortest path, which creates a heterogeneous distribution of traffic within the column. So that's the main objective from the comparison between JDTT and distance toll. So we provide this heat map to verify our conclusion, and you can see these are results from distance toll, and these are results of the JDTT. You can see this is more heterogeneous compared to this one.
Right.
Yeah.
I'm really sorry, but there's class going on.
Okay, right.
We're a bit late.
Yeah. Yeah. I think basically that I have introduced the framework. Basically, what I left is just some more sensitivity analysis, or yeah. Yeah.
Sorry.
So yeah, that's all right. So, but I guess you have a basic idea of what I'm doing, so that's good. Yeah.